Okay, so we can start. Thank you very much for being here for this presentation on the report of the global state of water resources by the World Meteorological Organization. My name is Giulio Castelli. I'm a researcher at the University of Florence, and this webinar is organized primarily in the framework of the Master of Science in Natural Resources Management for Tropical Rural Development of the University of Florence. So we will give also some information for our students, what's the meteorological organization and how does the reporting works, but is also co-organized by the AG-WaMED Prima program project. We have with us Dr. Sulagna Mishra, thank you very much, and also thank you to Nilay Guru for organizing this event. And for some more detailed information, I'm giving the floor to Professor Elena Bresci in Florence, who is the coordinator of our water harvesting hub and also the principal investigator of AG-WaMED project, besides being a teacher at the Master in Florence.
Okay, so thank you, Giulio. Good morning to everybody. Thanks a lot for being here. And first of all, thanks a lot for being available to Dr. Sulagna Mishra, because I think it will be very interesting for not only the students that are with us here in the room, but for all the audience. So I will just introduce who we are, just a few words.
The slides with the black screen. So you should go to display settings.
You need to turn off your mic. Don't you?
Come dice Giulio?
Yeah.
Proviamo a condividere.
Whenever you want to speak.
Yeah. Display settings. Duplicate slideshow, the second one. Perfect. Thank you.
Sorry.
So the Water Harvesting Lab has been established in 2017. It's a laboratory within the University of Florence, and it has been established mainly for doing research in the field of water harvesting and water harvesting implementation, rainwater management using GIS application. And we work a lot with in the project funded by some entity for international cooperation, and we are working in arid and semi-arid areas. The water harvesting definition that we adopted is the one given by OWES as the process of concentrating precipitation through runoff and storing it for beneficial use. So the countries where we are working and we had experience have been Italy, Nepal, Ethiopia, Mozambique, Niger, Burundi, Angola, Tunisia, Egypt, Bolivia, and Guatemala. And we had project funded by the Prima Foundation, EuropeAid, Italian Cooperation Agency, and Erasmus Plus, and in addition some other consultancies. So we are thinking that participatory approach is important for spreading and improving the utilization of water harvesting. We are studying the effect of water harvesting, in particular through the ecosystem services and the effect on the microclimate. We worked on fog collection, so the possibility of using fog as a water resource in areas where mainly advection fog form. Then we worked in Ethiopia with the flood-based farming system, and we tried to improve the possibility of diversion, a quantity of water without having problems in the diversion. We started the hydrology of the ephemeral rivers, the Wadi, and also in terms not only of the hydrology, but in terms of water conflict. And we have been involved in the evaluation of the ecosystem services related with water and the natural-based solution. We are also managing, because I'm the editor-in-chief of a journal, so the JIDE, the Journal of Agriculture and Environment for International Development, is a journal with the impact factor, and it is, the important thing is no fee for publishing in this journal. Two words on AG-WaMED. AG-WaMED, the full name is Advances Non-Conventional Water Management for Innovative Climate Resilient Water Governance in the Mediterranean Area, has been funded by the FRIMA Foundation through national funds. It is a 36 months long project, and we are almost at the end, because the project will end in at the end of August 2025. So we have 8 partners involved and 7 countries, with 4 living labs in 5 countries, because one of it, so the one that is established in Tunisia, Algeria, is a transboundary watershed that we are working on. Then we have the other 3 are one in Italy, in Val d'Orcia, the other one is in Spain, in the district of Cartagena, and another one in Egypt, in the Marsa Matruh area. So the project is based on a transdisciplinary approach, because we wanted to integrate the state-of-the-art of land, water management, agronomic issues, and policy, because we will arrive to the development of a pilot management plan for the use of non-conventional water, due to the problem of water scarcity that these areas are facing, through the involvement of stakeholders in the 4 different living labs. So these are some pictures, and the main objective is, as we said, the participatory management of the use of non-conventional water, and we want to innovate the use of water resource through the non-conventional for crop production. So we are using models for helping us to identify which are the main drivers of the use of non-conventional water. And we want also to work at the watershed level, because of the necessity of using the approach of integrated watershed management. And we are now in the phase of promoting the results of the project in terms of communication and dissemination activities. And I think that we have we are in a good track for really spreading the results of the AG-WaMED project. So for more information, you can go to the website of the project. So I stop here. I really thank you all, and I'll give the floor back to Giulio. One thing that I didn't say is for the questions, we will have a lot of time for questions. So please try to animate the seminar with questions. So we have 2 audience, one that is online and one that is here in presence. So we decide to ask for those that are here in the room to come and ask the question, and for those that are online, because it's much more difficult to identify the hands that has been raised. So please write in the chat, and we will go through. And if you want, obviously, the one that wrote the question, if you want to speak, we can give the floor and then wait for the answer. Okay? So thank you very much.
Thank you very much. And now let's give the floor to the keynote speaker for today, Dr. Sulagna Mishra of the DAGRI.
Thank you, Giulio. I will just take a second to upload my screen.
height. Yeah, you can height. Gonna height.
Okay. Okay. Hello, everyone. It's a pleasure to be here this morning to welcome you all to this to a talk on the state of the global water resources report, which is published by WMO annually. I'll take you through what is WMO, what do we do, what is the need of such reports, such global projects, why do we bring all this information together, what is the need, and how we plan to operationalize the whole thing, and how also this is helping member states to make better decisions when it comes to water resources planning and allocation. First, this is mainly for the students. When I talk to students, I find it interesting to give them an idea of my career so far and what I do at the UN. I come from India. My name is Sulagna Mishra. I have a background in civil engineering from BIT Mishra in India. I worked for a couple of years as a planning engineer in construction sector, after which I got a scholarship from the DAAD Foundation in Germany, and I did a master's in hydrogeology and environmental management. Post which I did an internship with Carlos as a Carlos Smith Fellow. This was in WMO back in 2015. This was a 6 months internship, but it also gave me a sneak peek to what how the system of the UN works and alternate career options. At that point of time, I was looking into various career options, so this was really helpful to give me options and show me how things outside of academia and corporate sectors work. From 2016 to 2021, I did my doctoral research, and I was also a postdoctoral fellow. This was in TU Dresden in Germany, and it was in collaboration with Purdue University in the US. Post my postdoctorate, since 2021, I have been working as a scientific officer in Hydrology, Water and Cryosphere division here at WMO. I'm based in Geneva, and what I do is very much related to what I studied and did my research on, and this is why this also makes my work here very interesting. So now going to the work I do here and giving a few results from the State of the Global Water Resources Report and a few other projects that I coordinate here at WMO. We know that the hydrological cycle is changing, and it's changing very, very fast, and this is changing due to various factors. One of them being the climate change. We are all talking about climate change, the rising temperatures, and so on, but this also has a massive impact on the hydrological cycle. The glaciers are melting faster, the precipitation patterns are erratic, and hence the results that we see in the hydrological regime is all changed. And this makes it all the more important to actually start to monitor all these changes so that we are well prepared for how we are going to adapt and mitigate the situation. A few slides on backgrounds. So we have more and more drought risk. We know that almost half of the globe lives under water scarce areas, at least for 1 month of the year. And this is based on World Water Development Report 2018. And since the number has changed drastically. It has gone even worse. Again, this is a Nature paper from 2022, which shows that almost 2 billion people are exposed to 1 in 100 years flood, and this is also not getting any better. In the maps you see here, the more greener the areas or the more bluish the areas are, the more exposed they are to flood risks. And this is not concentrated to one specific area. You see that this is really well spread, and it goes beyond the economic demographics and so on. It's not just underdeveloped or developing countries that are in flood risk, but it's really everyone. Nobody is spared from the wrath of climate change and the impacts it has been having on the extreme events. But is this really seen in our national priorities? Are our leaders, are the heads of the states aware of this? To find this out, our colleagues from the Water Policy Group in 2023 just before the UN Water Conference, they did a study where they spoke to 92 heads of states from all over the world, and they tried to find out, in their opinion, according to their national priorities, what are the greatest risks that they feel they are facing to maintain and achieve good water management in their countries. And this was independent study done for 92 countries, and the heads of states or the climate or water ministers were asked this question, and this is what the results we have. So it is identified that the top 4 needs are really the top 4 risks are due to climate change, due to increase in demand in certain areas. We see more and more people moving towards the urban areas, hence putting unprecedented demand of water in some areas in comparison to the others, hence affecting the distribution. And then we have the droughts and the floods, which are also well identified as risks, which are not letting the countries have good water management in their own countries. So this is identified. So what are we doing as UN? This was since many years. We had the first UN Water Conference after 46 years. This was done in March 2023, where all the countries came together. The conference was attended by more than 2,500 people, including member states, intergovernmental organizations, UN entities, and many other stakeholders. We had 11 heads of states, 120 plus ministers, and more than 166 member states delivered statements on their water ambitions. And this all shows that there is really an increased awareness and a priority setting, which is bringing water more and more into the picture in the national priorities and policy making as well. So what do we do at WMO? WMO was set up in 1950. It's the successor of International Meteorological Organization, which was existing since 1973. We are the authoritative voice of the UN. We are the specialized agency of the UN. We are the voice on weather, water, and climate, and our mandate includes to facilitate worldwide cooperation when it comes to the field of meteorology, hydrology, and their benefit. We also promote rapid exchange of data and information. This is absolutely necessary to be able to understand the status of now, and also understand how this is going to change in the next months, weeks, and in the next days. We also promote standardization of the observations, so that when we are comparing things across different basins, across different boards, we are actually comparing the same things against the same standards. When it comes to hydrology, we are focusing on operational hydrology, which is absolutely necessary for development, for example, for water management, for policy formulation, for agriculture, and at the same time, absolutely necessary for disaster risk reduction and mitigation and prevention. We encourage research and training by making sure that we're assisting the cooperation between the different parties when it comes to international arena. What we do is necessary to reach the goal for early warning for all. If you remember, the Secretary General of the UN, a couple of years back, he made a statement that by 2027, we would like to have a world where every single person in the world has access to early warning when it comes to disasters. And what we do is absolutely necessary to be able to reach and give out early warning. We need to have the data of now when it comes to meteorology and hydrology. We need to know when the floods and the droughts are coming, or if there is going to be any availability issue of water, and only then you can make the right kind of planning and make sure that everybody has early warning in the right time, so that they're able to take the right action. In WMO, when it comes to hydrology, we have 8 long-term ambitions. Of them, I'm going to focus on 2 of them, based on which I'm going to show you some slides later. So we focus that high quality data supports science, and we also want that science provides the sound basis of operational hydrology. So we are promoting that the policies that are made in the countries, the decisions that are taken in the countries are based on operational data that is available, and this is all supported by the state-of-the-art science. We know that water information, water data is critical for every department, or every information that you, what is the right word? Every field that you're working on, for infrastructure, for climate analysis, for WASH, agriculture, disaster risk, mining, for trade, for tourism, for everything, for food security, for peace and security, we need water information, we need the data. However, in many cases, because of geopolitical reasons, water data for national priorities as well, the hydrological data is of course most wanted, and we know that the countries identify this as something that is most wanted, but this is often not openly shared, nor it's available. And we know that from the data, from the surveys that we have done, this was done in 2021, we know that 2/3 of the national monitoring services, there is a decline. Countries are investing less and less money in situ data, in monitoring networks for water level, for discharge, for groundwater, and so on. When it comes to declining networks, it's not just with surface observation, but we also see this declining network with hydrometry. And this is not a good sign. And this is then where reports like what we do, the State of the Global Water Resources report, comes into play. What we do here is we do not let the limitation in the availability of in situ data stop from making a global assessment, but through reports like this, we show the value of having properly monitored data, and what kind of information and what kind of gold you can really get out. By gold, of course, I do not mean physical gold. Data is gold, is what we say here in WMO. What kind of information is you can really get out of the long-term time series, or the long-term in situ data that you are collecting. So to do this, we make sure to use innovative methods, because there is a lot of gaps when it comes to hydrology, not just in surface water, but also in monitoring of groundwater, in soil moisture, you name it, and there is a lot of gaps in the data. So what we do is bring together global hydrological modeling community. We bring the remote sensing data. We have an Earth system approach here. We put together all the data that is really available into the analysis, and we come up with a quantitative overview of how the water resources looked for the globe in the different basins in the last year. And this is an annual report, and we published this around the mid of next year, because of course it takes time to collect all this information, to validate them. We then of course send it also to the members to have a look and have a chance to comment and review the report. And only then we publish, only after all this peer review process and a heavy review by the members, we then publish the report around August, September of the following year. And this report has been very well received by the members, and the not just in terms of increase in engagement from the members, we also see that more and more data is now being monitored and also being shared. So in the report, we try to cover the entire water cycle based on the data, of course, that we have. Currently, this is how it looks. We cover the terrestrial water storage. The data comes from remote sensing. We have snow cover, glaciers, evapotranspiration, lakes, reservoirs, soil moisture, groundwater, and river discharge. So pretty much we try to cover the whole picture. And this year, in the reports, we are in the 2024 report, we are also going to have a chapter on precipitation to show what is coming into the water cycle and how then this is distributed across the different variables. And we will also have another chapter on lake levels. So as I said, the report is growing, and this is again an example of getting people in by doing, or as we say, leading by example. When we started in 2021, we had 7 countries on board. We had very few river discharge stations that had shared their data. For groundwater, we had 0 data that was shared. For river discharge stations, we had 14 stations globally that shared data. and in total we had 3 variables. From 7 countries being a part of the report, we are now at 54. You can see the change also in the number of river discharge stations that has gone up, and same for the groundwater stations. We went from 0 to 35,000 in 3 years, and in terms of variable as well, we have more and more coverage that we now see in the report. So the report is growing, and at the same time, it's not just the coverage that is being grown, but also amount of data that is being shared, and the interest that we see from the countries to participate in these kind of global initiatives that puts together all the data. But also at their national level, they are now more interested to create national bulletins and also regional bulletins. So this is not just only about a global report, but it is also showing the value of the added value of having such analysis done at a regular basis can help, how it can help them with integrated water resource management and planning. This is just to give you an idea that we have used various kinds of data. So we have model data, observed data, remote sensing data, and based on what kind of data is being used. For example, we use GRACE data from the GRACE mission of NASA. We use the terrestrial water storage, and this is where we have a bit less of historic time period of data. Usually we try to have around 30 years of historic period against which we compare our up-to-date data. And in some cases, of course, we have to settle in for a bit less. For example, for soil moisture observed data, the best case that we could have was 15 years, because beyond that, we just don't have the data at the moment. And the same goes then for terrestrial water storage. The GRACE mission was started in 2002. Hence, we have 19 years of historic data period against which we compare the current data, and we make the comparison. Of course, it is not possible to do any of this again, without our member states and a big set of researchers and organizations that have come together to help this. So this is really not a WMO report, but a report of the member states and all the contributors who have come together, maybe NASA, from SMHI, from all the data centers we have. This is really a truly global example of what we can do when we put our heads together. Now, how do we show the results? As I said before, hydrological data sharing could be geopolitically very, very sensitive. So many countries would like to share the data, but they're not comfortable when it comes to showing the numbers on the graph. So what we do here to overcome these challenges and to make things simple, not just from the geopolitical sensitivities point of view, but also in terms of simplicity of the report, because everybody that is reading the report is not a data scientist, is not a hydrologist, is not an environmental scientist. So we want this report to be as easily understandable to policymakers and also as easily graspable, for example, for the media and common public. So what we do is we change the numbers to colors. So we do a very simple statistical analysis. What we show here is a comparison of, this is, let's say, for 2023. So what we do here is we compare how did 2023 fall in comparison to the 30 years average. So was it much above normal, and the normal is defined from the historic data. So we compare, is it much below normal or above normal, and we give different colors, and we keep this consistent across the different variables. So it becomes easy once you grasp the definition, it becomes very easy then to understand what the different variables look like. Now coming to the river discharge data, as you can see here, even after the 3 years and 54 countries on board, you see large data gaps. And how do we overcome this is with a lot of global modeling data. So one of the very interesting results from last year, which grasped a lot of which grasped a lot of media attention, was this one. This is showing that 2023 was the driest year on record for global rivers in more than 33 years. We say 33 years because that's the on-record data that we have. And as you see here, the more towards 2023 that we are going, the more recent the years are. In the last 5 years, we see a significant decrease in the area that is under normal conditions. So we are going into more drier and wetter conditions, and less areas are exposed to normal conditions. And 2023 was the least normal, and at the same time was the highest, was the year where we saw the highest number of area or highest distribution of area that was under brown conditions, which is dry. For the records, 2023 was also at that point, 2023 was also the hottest year on record. We just published a report, we just published the news a couple of weeks back that 2024 is now the hottest year, but when this report was published last year, 2023 was the hottest. And just to highlight that the hottest year temperature-wise also translated to the hottest year what we saw in the availability of water, and hottest year that our rivers show. So the hottest was also corresponding to the driest. This result here, what you see is a complete picture of the globe. So we filled in the gaps that you saw in the in situ measurement, which was a half-empty global map with results from 10 global operational hydrological models. So it's an ensemble of 10 models put together. This year we are going to have even more. And what we show here is how did each of these basins, so we have we follow a classification based on the DEM, and we show here how did each of the basin compare to the hydrological normal of that particular basin. So I have circled a few areas here just to highlight that when we have reports like this published every year, when we compare one against another, so if you compare 2023 against 2022, you see which are really the hotspots. What did the impact of the precipitation or the snow have on, let's say, in stream flow for particular areas? So the first one here I would like to highlight is Colorado. So you have in the West Americas, you see a big spot of blue, which was a consistent drought since the last few years, which went off with 1 year of heavy snowfall. We see this in the SWE, in the snow water equivalent map as well. In the SWE map, we see that Colorado received a very heavy snowfall. And you see that translated into stream flow in this. So when we have reports like this covering the entire water cycle, you can also corroborate what precipitation means in some areas, how did the climatic regime change, and how did that impact soil moisture, for example, or how did that impact the groundwater. And this helps the policymakers and the decision makers to take the right kind of decision, and also understand how the signals, the climatic and the hydrological signals, how they reflect in their particular basins. This next one here is an example of La Plata Basin. You see that it's a drought still. We were expecting to see a more wetter condition or a more normal condition. But however, in spite of the change of La Lena to Elena, we don't see any of these changes in 2023 yet, but we expect to see this in 2024 report probably, with the more rains that came in later in the year. Similarly, we have the Great Horn of Africa, which had a long persistent drought for a few years. It was also seen in our older reports in 2021, 2022. We saw a drought in Greater Horn of Africa, but with one heavy rainfall event or with one heavy rainfall season, you can see that this changed from drought conditions to the wet conditions. So what this helps us do when we make this kind of consistent and standardized report is help us in find hotspots, which ones are really due to climate signals, which ones are rather localized, and so on. Similarly, we have reservoir inflow, which kind of gives us an example, or it gives us an idea of how much water is actually available for the ecosystems and the societies. The total terrestrial water storage is the sum of all the water that we see, all the fresh water that we see on the ground. So sum of groundwater, soil moisture, river, lake, reservoirs, snow and ice storage, etc. So this is from the satellite data, and this also helps us understand if there is a certain area which is let's say deep dark brown. When it comes to terrestrial water storage, there might be a case that we see an opposite signal in one of the other variables. So this is then giving us a hint that probably the stream flow was not so much, but we might have seen more increase or more decrease in the groundwater. So it helps us to disentangle the different variables and the signals between the different variables and understand what happens in the total submission and what happened in the different parts of the water cycle. I, of course, do not show all the results here. We have maps on evapotranspiration, on soil moisture, on groundwater, and SWE, the soil snow water equivalent. I do not show all the results here for the sake of time, but I welcome you to have a look at the report and also at the previous reports to see and compare how things have changed over the years when it comes to our hydrological regime. We have a map on the high impact hydrological events, which gives us an idea not just of the floods and the droughts, but also we let countries identify which were the events that were unprecedented in their record. So they might not have made to the top list when it comes to the global standards of high impact events, but for their region, this was something that they have probably never seen before, and this is also alarming. So this we also try to include this in the report. Now, this year being the International Year of Glacier Preservation, of course, you must have all heard about the fast melting of the glaciers. 2023 was on record the highest loss of glacier mass that we ever saw. So we saw 600 gigatons of glacier mass that was melted away in just one year. That was 2023. Now, this report that you saw is a one-time thing that we do once a year, and it gives you an idea of what happened in the last year. But if we want to use such reports or such data, this data is of course very interesting and useful, but if we want to use it on a day-to-day basis to make decisions in our let's say water service, or if you're a dam manager, or if you're a water minister and you want to make decisions, you cannot depend on a report that comes out half a year later to take decisions for the following year. So what we do at the same time of having this report is also capacitate members to make these calculations by themselves. So the status calculations that you saw, we do capacity development programs, we share meteorology documents, and we let them also learn to how to do these calculations themselves for their national reports, for their national bulletins, for their national decision making. And at the same time, not just the status, we also capacitate them to make outlooks, so seasonal, sub-seasonal outlooks, which will then help them to understand how the things are right now when it comes to the different water variables, the stream flow, groundwater, whatever they think is important for their basin, and how this is changing in the next weeks, in the next months, and maybe over the next season. So depending on what kind of seasonality the countries and the basins see. So we put together the ground-based observations, remote sensing, weather and climate forecast. We use hydrological models, of course, and at the end, the idea is to put together a web-based product, which is then integrated across scales. So when you have one portal that shows all this information, when you're comparing two separate basins against each other, you are actually not comparing apples with oranges, but really comparing things that have been calculated in a similar fashion. So we put together all the national, basin scale, regional products and global products wherever there is a gap. For example, there are many countries, they do not have enough data to make a national prediction. So it makes rather more sense to have a basin product and downscale it. And in some cases, even basin products are not possible. So we do global products and we downscale them to basin scale. So the idea is to have a standardized and accessible and products that are interoperable. So this is HydroSOS, the hydrological status and outlook system. Currently, we are implementing it across many countries, and the idea is to have globally consistent and accessible data and information, not just for the nowcasting, not just for showing what is happening now, but also with the predictions. So what does it provide? It shows us how is the current status. Is it normal? Is it not normal? Is it much above normal? Just like what we did in the water report for the yearly basis, in the HydroSOS, we try to do it more frequent. So weekly, bi-weekly, and monthly, for example. And then we show an appraisal of if this is going to change or get worse or better in the next weeks. So in this picture, which shows the entire value chain, for example, from going from observation and data management to the whole, all the way to save lives, reduce losses, and improve livelihoods, we come in the 3 blue dots here. So we do the analysis, modeling, and forecasting. We try to produce standardized hydrological information and products, and we make sure that this is then disseminated and communicated to the member states in the right format, in the way that they can understand, and in the way that's most suited for their community. So we have a global platform, global portal. I'll show that in a minute. We have a global platform where all this information is available, but then we also encourage the member states to do bulletins, which then reach out to the member states or send out emails or SMSs, really depending on how things work best in their setup. So this is a map of where we are with HydroSOS, this operational system, and we are, as you can see, in many countries currently implementing or at some stage of implementation. At the moment, we are at 60 plus countries trying to operationalize hydrological status and outlook systems in a very standardized fashion. This is the portal. I would still like to call it a beta version. It's not fully operational because we do not have data from all parts of the globe coming in already weekly or bi-weekly yet. But what we have in the background is global products. So these are global hydrological models which are in the background, and then the idea is to have a top-down plus a bottom-up approach as well. So data coming in from the regions, from the members, and data coming in from the global global models to support this data. So the members can get the best quality results. So this is the last slide. What is the added value of these science-based products? Why do we focus so much that whatever we do has to be science-based, whatever we do has to be based on data, and all the decisions are made based on data. It gives us global overview, and it gives us graphical summaries which make it very easy to understand. When we do it from WMO at a global scale, it is standardized, it is consistent, and it is authoritative. We have when we do independent assessments and do not so at this scale, for example, when we do it as WMO, we do it as an independent assessment. It helps us in identifying hotspots. I gave you some examples when I showed you the results. So identifying those kind of hotspots helps us to make global decision when it comes to large scale planning and where, for example, where we should be investing more and so on. It enables us to do interannual comparisons to differentiate which one is really a short-term impact, which one is a long-term impact, and how the water distribution is being affected. And at the same time, when you look at the larger scale, it doesn't only impact and affect national level planning, but it also informs and guides intergovernmental discussions and larger international discussions, especially in shared water resources. And that was the last slide, and I would like to open the floor for questions.
Thank you very much, Sulagna. And we have now the space open for questions. So I remind you, if someone on the audience wants to keep questions, please drop a line in the chat. Otherwise, we are also waiting for questions from the room with our students at the University of Florence. And in that case, you can just go to Professor Bresci and ask to speak.
So thank you very much for this interesting presentation that I think will make the a lot of thinking for each of us, depending on the background and also the competence that we have, since there is a lot of people over here. So first of all, I will ask to the students that are here in class, in the room, if they have any, first of all, clarification requests, comments, or questions. Yes, please, can come here. So we have...
Maybe we can activate the camera and then the student can introduce.
Yes. So please present yourself.
Yeah, good morning together. Thank you for the presentation. My name is Moritz Jeka. I'm a student from the master degree in natural resource management for tropical rural development here in Florence. And I was curious if you could be more elaborate on the modeling for hydrological patterns, especially because I saw in the graph that in Southern Africa, particularly South Africa, there was, I think, positive trends visible, which, if I remember correctly, I saw in IPCC models being the opposite. So just out of curiosity, I would be interested maybe how these models are made and which time horizons are those models looking at when it comes to prediction. Thank you very much.
I don't know if there are some questions from the room, but shall we get the first three questions together? There are two more in the chat. So this question, the first question, thank you, was about basically the modeling strategy and like our students also referred to this IPCC modeling for Southern Africa. And then there is one question from Livia Serrao. Maybe we can open the question also here in our laptop. This is the second question. Sorry, try to put it here. I do not know if it's been mentioned. I'm curious about the way national hydrological data is collected. How does WMO deal with the differences? And where are the river discharge data source? So that's more or less the same. So let's get these three questions first, and then we move on.
Thank you very much for the questions. Just to clarify, what the maps that I showed here was not on prediction, but it is only the status. So how did 2023 look in comparison to the last 30 years of data? When I show these modeling results, one second, yes. So when I show this modeling results here, we also do, for wherever we receive the in situ data, we also do a validation process. So if you see something different in the models that in comparison to the in situ data, then there is a possibility, of course, but what we saw that based on the data that we received, there was a more than 90% accuracy of the models. So the models that we are talking here are the operational global hydrological models. So let's say EFAS, GLOFAS, SMHI, models from NASA, models from UFZ. So I would say the best global hydrological models they basically are put, of course, the ones that could come to us in time. There are more than 10 global hydrological models, of course, but we used 10 in this study that you see here, and what you see is the status, not the prediction. If that answers your question in comparing South Africa. But if you see here, when you see South Africa, you see a large part on the ground that's more than average, and if you compare it here with the data that you have, it's also the same. So if you see South Africa in situ data, it's also more than average, and if you compare this with the model results, this is also more than average. So South Africa, if we are specific about South Africa, the results match. With the IPCC result, I'm not sure which map you are referring to, but if it's something with the prediction, then this is not really, we are not comparing the right things here. So that was one. The second question was about how we collect the data, how is it coming through to WMO, and how do we deal with the inevitable differences in the units of measurement. This is really a very good question. So we have WMO supports and has set up many data centers, global data centers, not just for climatology and meteorology, but also for hydrology. So we have the GRDC, the Global Runoff Data Center, which collects hydrological data for river discharges. We have IGRAC, which is the data center for groundwater. We have ISMN, the International Soil Moisture Network. This is collecting data for soil moisture. So we really encourage our member states. We have an open data policy. So we encourage member states to collect data and to share data, to make data available. Because really with the time of machine learning and AI and all the remote sensing products that we have, it's really no longer a secret. If members do not want to share the in situ data, anyhow we will find the information from the satellite data or from modeling data and so on. So it's really, we encourage data sharing. So what we do is collect the data through data centers, and the data centers have their basic tools in place to work with the different units that there are, different disparities. They also do a quality check, though member states also do a quality check before they send it to the data centers. But the data centers also have a quality check in place before they collect the data, and then they make all this data available to us, usually in a standard format. Everything that is coming through the data centers to us comes through a very standard format. So this is already filtered. So this is less work for us. But then there are member states who do not want to share the data with the data centers, but they directly want to be a part of the report or of HydroSOS, and they send us the data directly. So this is then where we at the Secretariat have to work with the disparities in the different units that there are. So this is then work for us. To bring them to a right format, to homogenize, to make it uniform, and then use the data ourselves. So to answer your question, we do it both ways. Coming through the data centers do the work for us, and when it comes to us directly, then we merge. We do it ourselves, and then we merge the data that is coming from the different sources. For the modeling data that is coming to us, we have a data protocol. We send the protocol to all the modeling centers out there, and whoever can send us the data in the right time that is then used for the publication of the report, we use them all. And usually from the modeling centers, because they're all coming through codes, etc., usually this is all homogenized. We sometimes have to do a little bit of tweaking here and there, but usually this is homogenized, and it's not so much extra work to homogenize the system. And the second question was again about the river discharge data source. We get it from whatever source is really available. Member states sometimes send it to the data centers, we get it from them, or they send it to us. Or the last option is also, if it is already available through some kind of API or in their website where we can directly fetch it from, we ask the member states to give us the link, the official link to these sources, and we get it from there. So we do not get data, for example, from papers that is published or so on, which is also rare, because by the time we are working on the report, the data from the last year has not been used for any of the published papers. So, but it has happened in the past that some data, at least for half a year or so, has been available. So we scrape the internet for everything that is possible, and then we confirm with the member states if this is official data or not, and then we use it. If that answers your question. Thank you.
Thank you very much. We have questions from the audience.
Are there any other questions here in the room? No? Okay. We have one question here.
Good morning. My name is Antonio Santoro. I'm a research assistant at the University of Florence. And thank you for this presentation, and thank you to the organizers. We know that agriculture is one of the main activities at the world level with high levels of water consumption. And I'm wondering if there is some kind of experience in trying to connect this at the global level, this water assessment with the different type of agricultural activities that are actually carried out in the different countries or different water basins. Thanks. Thank you for your presentation again.
We do this one and then one by one because they are a little bit different.
Yes, I can do. Yeah, we can take this. Thank you for the question. Yes, we know that almost 70% of the water is on an average. Almost 70% of water is actually used for agricultural purposes, and in some areas even more than 90% goes to agriculture. But it's not the mandate of WMO to look at the different agricultural practices and how this impacts. What we do look at, which are the areas where we did see heightened signal when it comes to water, groundwater pumping, for example. But before publishing this kind of attribution studies, we make sure that this is something that is published in literature. To answer you in short, we do not do the attribution of what practices use more water than the others. This is something that is under FAO, the Food Agriculture Organization, which is based in Rome. This is their mandate to look in details into agricultural practices. But what we do is how we see the signals of or which are the areas that we see a heightened decrease in groundwater, and then we say maybe this was because of over extraction, but we do not say if the over extraction was because of industrial practices, or was it for a factory, or was it for agricultural practices. We do not do the attribution for that. It is just out of our mandate.
Thank you. And now I think they sent me a message. There are no other questions from the audience in person, but we have, I think, at least two more. The first one is by Awais Naim Sawara from University of Naples. It's about terrestrial water. I've noticed that it's much lower in snow-covered regions worldwide. I'm wondering why we are seeing this trend. I don't know if...
I have noticed that there is much lower in snow-covered regions worldwide. I'm not sure if I understand the question right. Do you mean that there is less snow regions globally, or there is less terrestrial water storage in snow-covered regions?
Maybe otherwise, if you can write down an update of your question, and then we pass to the other one.
Yeah, we can do that. Do you understand that question?
No, I think I understand more or less like you, but
okay.
Maybe otherwise, if you can further explain a little bit.
It could be that why. Okay, maybe I understand it now. Maybe he means why is the terrestrial water storage less in the areas which are usually snow-covered?
Yeah, possibly. I think this is the
question. No specific reason for that actually. In the last years, we know that specifically in the snow-covered areas, in the glaciers and so on, in the we have 19 glacier regions globally when we put them together, for example. So we have seen that in the last years, more and more glaciers, because of global warming, they are melting away. In the last 3 years, we have seen that consecutively the last 3 years, all the 19 glacier regions are losing mass. So this is one signal why we have so much less terrestrial water storage. But terrestrial water storage is not just glaciers, it's not just snow, it is a combination of all of them. But in areas which have these glaciers have a significant impact. So this could be one of the reasons that why specifically in these areas you see the delta and the anomaly is very high. And more towards going brownish than normal and above normal because of the excess of melting glacier. But this is not the only reason. And to be more specific about the reasons, we have to be specific about which area we are talking about. For example, when it comes to Russia, for example, or it comes to the southern Canada and northern USA, for example, in these regions, we know there are other factors as well that are affecting why terrestrial water storage is changing. So we have to be a bit more specific, but yes, glacier melting is one of the major reasons why we see less one glacier melting and also less snow. So when you compare this map with the SWE map, the snow water equivalent map, you also see the corroboration between the areas and how these two factors also relate to each other. So less snow, more glacier melting, plus other reasons on the top of it.
Okay, thank you very much. We have the final question on photovoltaics and water availability, and then I will make one final question and then we close.
Okay, thank you. So have you studied the impact of solar photovoltaic cells on water availability and solar PV covered built up ground from preventing evaporation and drying of soil? These impacts, of course, they will have an impact, but solar photovoltaic cells, they whenever they are covering, they're not covering like concrete. So they have a tilted areas, so the ground beneath still receives the water. So when we have a rainfall event, for example, and there is a photovoltaic field, we do still receive water. Water still seeps in because of the angle, and it does receive it does reach the soil. So we should not see a very large impact on groundwater availability because of this, or amount of water that is being seeped in because of this, but definitely it will have a larger impact on evaporation. So because of the tilted surface on the top of it, it stops or it prevents evaporation. But then this effect is very localized, only in the areas where we have the photovoltaic cells, and I do not expect to see a very huge difference in the patterns when we are talking about a big hydroshed area, which is more than 10,000 square kilometers. I do not see all these hydrosheds area that you see in the map is actually greater than 10,000 square kilometers. That's how we define them. So in this kind of scale, I do not expect to see a large impact of photovoltaic cells, which are rather very, very localized and very local. But for that area, for that microclimate, it will create a difference, of course.
Thank you very much. I think we have a question from Professor Bresci from the audience. If you want to use the mic.
Yes, thank you. Thank you again for the presentation and the very interesting discussion that came out. Since the project in which this seminar has been in was non-conventional water, I was wondering if you are working on the non-conventional water use at a global level. Thank you.
Non-conventional water uses.
Yeah.
Could you define?
Yeah, non-conventional water is the topic of our project. So it means water harvesting, desalination, wastewater use. So it's just a question. I had also another question, but I will mix it. How you account for these non-conventional waters, and if there is some relationship, and like at the larger scale, how can our project support you, or if we can interact in some way?
Thank you. Yeah, unfortunately, the non-conventional water use is not at the moment at this scale that in this large basins, it will have a significant impact when it comes to a comparison with the normal, etc. If you, of course, we support, or we know that there is many nature-based solutions like the managed aquifer recharge, like desalination being done, excess of desalinated water or treated wastewater, for example, being used for managed aquifer recharge. But here at WMO, we do not work directly on projects on this. But of course, the grey water and all of this, we would like to take into account. But unfortunately, the data that we have at the moment operationally available, not from research projects, but something that is more sustainable and more operationally available, has been very limited in the past. We know that at global scale, there have been a few projects also from a remote sensing point of view that have a look at these kind of grey water, for example, and treated wastewater being collected, but we haven't used it on a regular basis in our operational products so far. Having said that, some of our models look into water usage. Not all. For example, there's a model water gap that looks into water usage as well. So taking into account how much population is there. So empirically trying to connect how much water is being used, how much water is actually being again thrown back into the water sources after after being treated and so on. But this is, again, not all models do include this factor as well. So to answer your question very short, no, sorry, we do not use it so far, but this is something that that we would like to eventually.
Thank you. Just to close, official closing. So this is a very nice presentation done to students and also projects and so on. If you can give us a very, very quick keynote and final message, how we can use the report in a more operational way in our research activities, but also how, like, university, especially one that works in agricultural science, can support you in vice versa.
Thank you. Again, of course, two-way street. How you can use our report. Of course, the results are out there for you to use and refer to make connections, for example, of patterns that you see. For example, if you're working on groundwater, you can, through reports like this, you can have a look at if this is the trend that you saw on groundwater or in a very specific area, how did it look at a global picture, at a regional scale, and so on. So to scale up your results and verify these, the reports like this can be very useful. We actually did a survey, a user survey that was led by my colleague Nilay. We tried to understand how this report is being used, and we saw that 50% of the usage is actually coming from researchers as well. So a large percentage of many researchers do use the report to verify or validate their results and look at the bigger picture. This is one. And we also are very open to sharing all the data that we have collected so far. So this is, again, a gold mine of data that we are sitting on, but WMO, as you know, it's not an active research organization. So we don't write papers here. We collaborate with researchers, but we don't do active research. So if you would like to have your hands on the data and take it and basically make some nice results out of it, we will be very happy to share all the data that we have with you. Also the scripts, for example, as we say, we are open source, completely open source in all of the work that we do. So that's one. And the second one, how can you support us? This is the more interesting part for us, of course. If you're producing some results which is state of the art, which you think is of a scale big enough to be a part of the report or to be a part of the HydroSOS portal, and if your projects are sustainable, you think it goes beyond the research duration, and there is some way that you can sustain the results that you're sending us over a period of time, then you're very welcome to connect with us, and we will be very happy to take the data and use it in or include it in portals that we support. And at the same time, if you think there is a large-scale project that you're doing, which might not go beyond the research duration, we are also happy to do some kind of a case study or include some kind of a case study in our report. We have done it in the past also, just to show it to the member states, the value of having high-quality research being done and what added results you can see. But because as scientists, we all agree that what you see here is very, very pragmatic. We have really taken a lot of data and put it in a very, very simplified fashion, but we could have done much more if we wanted to reach a larger audience. If we have massive amount of data at a larger scale, we could have done much more. We could have gone into much more details and so on. So if you want to do that kind of a micro study for a certain area and show the added value of science and data, we are happy to include that as well.
Thank you very much. I think this was a very, very clear final message, and I will leave the floor to Professor Bresci for the final remarks, and I anticipate my thanks to all the audience.
Okay, so thanks again, because I think it has been really helpful and interesting, and not only for students, but for all of us, because as I said, there is people coming from different countries, different background, and different competencies. So I think really the message that you showed us will have really an important will be an important source of thinking for all of us and for all the activities that each of us is carrying on. So I'll ask you if you can not sharing the screen so we can have a picture of all the participants. So, and thanks a lot again, and I hope to that there will be some other opportunities for talking together. So I'll give the floor back to Giulio. Thank you.
Thank you very much. So yes, if you can open your basically camera, will make a picture, and then I will remove the recording, and you will find this online, probably on our project YouTube channel. Thank you very much, and again, really nice to have done this presentation and this activity in partnership with the World Meteorological Organization.
Thank you, everyone. Thanks from me as well. You have been a great audience, and always a pleasure to collaborate with students and also with projects and take it further. Thank you.
Thank you. Bye-bye.
Thank you.